Hello everyone, this is the lecture on inferential data analysis, part 2. In the first part we looked at t-tests, looked at the 3 types of t-tests. In this section, or this part of the lecture, we're going to look at analysis of variance, which is the second part of this module. So we know that many research problems or questions involve more than 2 treatment groups. And we talked about t-tests and how they can be used to compare 2 treatment groups. In situations that require more than 2 treatment groups, analysis of variance, or ANOVA, is used to analyze the data. And there's many different types of ANOVA designs. We're going to look at some of them throughout this PowerPoint lecture and try to plug in some examples to bring it to life. So just to review, in the last lecture we talked about techniques that allow us to make generalizations about the population, being termed inferential statistics, and we talked about one group t-tests, independent t-tests, and dependent t-tests. We also established that if the p-value was smaller than the alpha level, which is often 0.05, then we reject the null hypothesis and state that the difference is significant and not due to chance. So let's create some dummy data, and let's say we got 3 groups. Let's say we got 3 groups. Each column is a group A, Group B, and Group C, and there's 5 people in each group. Subject 1, Subject 2, 3, 4, 5. So here's the 5 people in Group 1, and then the second column is the 5 in Group 2, and the third column is the 5 people in the third group. So let's say that here's what we're looking at: the 5 people. Here's the sum of their scores. There's the average. So that could be some descriptive statistics here that gives us some information. But what we might really want to know is, are there any significant differences here? So just by plugging that information into Excel or into SPSS, it gives us this ANOVA source table, and we'll see a few of these throughout this PowerPoint. But what it gives us, instead of a t statistic, it gives us an f ratio or f statistic, this number here, and then this p-value tells us whether that is significant or not. So this is significant at the massively significant at the 0.00085 level. So there's differences there between those 3 groups. This is just a link to a table that shows you whether compares f statistics, f ratios to the p-values. You don't necessarily need to go look at that, but you can check it out by clicking on that link in the PowerPoint file on Blackboard. Also, I'm going to ask you, because I always play this YouTube video in class, so I'm going to ask you to watch this by clicking on the link, and I'll put it on Blackboard so you can get there directly too. This is fascinating, and I love showing this in class because it really shows you how ANOVA works behind the scenes. It really takes the data, and here's our 3 groups that I just gave you: Group 1, Group 2, Group 3. And it shows you how ANOVA works and how we come to those levels of significance that I just showed you. So I want you to watch that video. So why do we have analysis of variance? Well, there's a limitation to t-tests. T-tests can only compare 2 groups. And even though we could compare, or we could perform multiple t-tests to compare multiple groups, every time we do that it adds to what we call an error rate. So a t-test, ANOVA is an extension of t-tests that we use for more than 2 groups. So whereas a t-test would be perfectly fine to compare the 2 groups we talked about in the last lecture, which was comparing a 70% to a 40% VO2 max groups. Let's say we had 3 groups in that study: a group that trained at 70% of their VO2 max, a group that trained at 50%, and a group that trained at 30%. We could do multiple t-tests, compare the 70 to the 50, the 50 to the 30, and 70 to 30. However, that's not an efficient way to do it, because each time we do that, we increase the chance for a type 1 error. So let's talk about multiple t-tests and type 1 errors. Every time we perform a t-test, if we do it multiple times, we're multiplying the 0.95 by the number of tests to calculate the probability of not obtaining one or more significant results across all tests. So if we ran 2 tests, the probability of not obtaining one or more significant results is multiplied and ends up in 0.9025. So if we were comparing 4 groups, A, B, C, and D, we would have 6 of these pairs, 6 separate t-tests to run, and you can see those listed there. So therefore that increases the chances of incorrectly rejecting the null, which is a type 1 error. So instead of that being 1 in 20, it could actually be 1 in 4. So what ANOVA does, it compresses all those means simultaneously and maintains the type 1 error probability at the designated level. So that's a lot of detail. For this course, I'd just like you to recognize that multiple t-tests aren't efficient, that they increase the type 1 error rate, and that if we have more than 2 groups, we're probably looking at wanting to do ANOVAs instead of t-tests. So let's look at some different types of ANOVA. The first one is a simple one-way ANOVA. This is an extension of the 2 independent groups design already discussed, but typically involves statistical analysis of 3 or more independent groups. So when there's 3 or more groups, the best option is ANOVA. And this is like I said, this is an extension of the independent t-test. There's only one independent variable, but now we're not limited to 2 groups. So here's an example out of a different textbook. We have group 1, group 2, and group 3. There's the raw scores for each of the 5 people in each group. And then by plugging it into the formula for ANOVAs, and all of this is obviously mathematical equation based, by plugging these individual scores into the formula, you see that below here, we come up with this source table or summary table for ANOVA. And all ANOVA is doing is comparing some sum of squares and mean squares, looking at the differences or the variation between the groups versus the variation within the groups. So here we get this F statistic or ratio of 10, which tells us down here at the bottom that that's significant at the 0.05 level. So that's taken these scores from these 3 groups, and we've done a one-way ANOVA, and it's told us that though there's differences there at the 0.05 level. Let's go back to our football example. Let's say our players are divided into 3 groups, 3 different positions, and we want to see if the 3 groups are different on the dependent variable of the bench press. So there's only one independent variable here, that's position. There's 3 levels within that independent variable, and there's only one dependent variable, which is the bench press. And our null hypothesis would be that there's no differences, or there's no significant differences between those 3 positions. And we're setting our alpha level at 0.05. So we have 28 players in each of those 3 positions, and we can see on the descriptives up top here that the mean for the backs is 248, for the lineman is 318, and then for the 3rd position it's 250. Okay, so that's the mean or the average bench press 1 rep max total for these 3 positions. Now we could look at this and think, okay, that position and that position are pretty close, but this 318, that seems to be a lot higher than these other 2 positions. But what we really want to know, and that's that big question again, is are there any significant differences between the 3 groups? So those Those 28 scores are put into 3 columns in Excel or SPSS, and you can, hopefully at this point you've watched that video of how to do that in Excel, and it provides us this summary table, and then this is very significant at the 0.000 level. But there's something missing here. Okay, so it's telling us that there's a significance here between these 3 groups. I wonder if this point, if you can pick up what's missing. We'll come back to that. So our p value is lower than our alpha, therefore we reject the null and conclude that the groups are not equal. However, what it's not telling us is between which groups is there significance. All a significant ANOVA tells you is that at least 2 of the groups are different from each other. And to find out which groups are different, you have to do something called post hoc tests. So if we went back to this, the ANOVA is telling us that at least 2 of these groups are significantly different. Now, we could probably make a safe guess that the 248 to the 318, because that's the biggest range, there's probably a significant difference there. But is there a significant difference between the 250 and 318? We don't know. We could probably safely say not between the 248 and the 250. So we do these post hoc tests. We only do post hoc tests if we find a significant difference with the ANOVA score. Once we find that significant difference, we have to do these post hoc tests to pinpoint the location of the differences. And this is pretty easy. It's just another click on an option on Excel or SPSS. There's many different post hoc tests. Some are very conservative, some are liberal. Some pick up slight differences, some pick up big differences. For the purpose of this course, I just want you to know what a post hoc test is, and that we do them if we find a significant difference with the ANOVA. We don't need to do a post hoc test for a t-test, because t-test there's only 2 groups. You just look at the scores and you see which one's higher and which one's lower to make your statement. But when there's more than 2 groups, you don't know which ones are different. So here's some different names, and most of them are in fact they're all named after the people, mathematics or the mathematicians who came up with a slightly different formulas for each. The ones that I see most often use are the Tukey's or the Fisher's LSD. So let's look at that in a little example in SPSS. So here we have 3 people in each group, 3, 3, 3, and this is just a sample that I made up quickly. The mean for each group is 3, 4, and 8. Let's say they took a test where they're trying to get a score out of 10. So on the ANOVA table down here, here's our F statistic, and it's telling us that this is significant at the 0.48. So there's a significant difference somewhere between these groups. We just need to find it. So we run these post hoc tests, and here I chose Tukey's, and you can see that here the significant levels of 0.05 or less that we're looking for. It's telling us that the difference is between group 1 and group 3, which is the same thing as between group 3 and group 1. That's telling us where the significance is in those 3 groups. And if we go back to here and look at the mean score of 1, 3 to 8, well, that kind of makes sense because it's the biggest difference between the 3 groups. So let's look at another example, and this is an interesting one that I created a couple of years ago. Let's say we've got some data from different tires. Bridgestone, Goodyear, Uniroyal, Firestone, and Michelin. And this is based on the amount, I think it was the amount of miles that tires can go for before the wear and tear gets too much. And that's thundering outside, so I don't lose this lecture, I think I'm going to go ahead and produce this video right now to get it saved, and then I'll pick up the next one from this slide.